students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 10. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. In today's lecture, we are going to continue our discussion on specific properties of semiconductor materials, and we are also going to discuss some equations which are related to the conduction of current in various semiconductor devices. Okay. So, let us start. We will continue our discussion from the point where we left in the previous lecture. We were discussing how strain can be produced in semiconductors via heterojunctions and what are the major advantages of it. So, if you have a material say like silicon, right, if you have silicon material and if you deposit this thin silicon material on top of a large thick substrate, okay, this substrate can either be germanium or it can be an alloy of silicon and germanium. Okay. Silicon and germanium, if we measure their lattice constant, there is a 4% difference between the lattice constant. The lattice constant of silicon is slightly lower than that of germanium. So, when you deposit silicon on germanium, it tries to match its lattice structure and undergoes tensile strain. This tensile strain alters the energy band diagram. It increases the energy band curvature, which reduces the effective mass and produces high mobility, as mobility is inversely related to effective mass. So, when effective mass reduces in strained devices, mobility goes up. This is how you can produce high mobility semiconducting devices. Okay. But the idea here is that the thickness of this material, this thickness should not exceed a certain value known as critical thickness. The degree of lattice mismatch, the amount of mismatch which might exist between these two semiconductors in the heterojunction, that can be measured as the absolute difference in their respective lattice constants. So, lattice constant of the epitaxial layer minus that of substrate divided by the lattice constant of the epitaxial layer, that is the degree of mismatch. Half of the lattice constant of the epitaxial layer, that much thickness you need to have. Okay. So, this is the critical thickness. If this thickness is exceeded, the strain starts to go down and the benefit of high mobility is lost. Okay. So, you need to ensure that the thickness of the thin film on the top is below or at least equal to, if not below, it should not exceed the critical thickness. Okay. This produces a lot of performance enhancement. So, this is one way of studying the properties of semiconducting. Now, coming to the next part where we basically start this lecture of today. Now, strain in junction can be measured in 2 dimensions, but when dimensions go down, the physical dimensions go down, there can be different types of structures which can appear. They can be broadly categorized into the category of nanostructures. Okay. And an important application of this, which and nanostructure is nothing but basically an application of a heterojunction only. Okay. So, a junction between two dissimilar materials, but the relative dimensions are actually lower. Right. So, to use the differences in the EC and EV, the conduction and energy band levels, these changes in the relative energy band diagram can form barriers for carriers. Okay. So, your charge carriers, electrons and holes, can encounter local barriers within a semiconductor material. One such arrangement is known as a quantum well, which is formed by 2 heterojunctions, or it can also be formed by 3 layers of material such that the middle layer has the lowest value of conduction band energy. Okay. For an electron well, or the highest valence band energy for a hole well. Okay. So, by well here we mean a barrier. We have discussed potential wells earlier, and that was nothing but a potential barrier which charge carriers experience. Okay. So, a quantum well, what it does, it confines electrons or holes in a 2-dimensional system. Okay. And you need to apply a certain energy such that this barrier can be surmounted and conduction can take place. when electrons are free to move in a bulk semiconductor in all directions 3 dimension, their energy above E c is continuous. So, if E is the energy above E c, so E minus E c is the energy of a charge carrier, energy of an electron inside the conduction band is given by this equation here. Okay. The origin of this equation is in kinetic energy half of m v square, and v you can relate with the momentum. Okay. So, this k here is nothing but the wave number. Okay. In 3 dimension. This is the wave number in 3 dimension in x, y and z, and we know that k is actually proportional to the momentum. Okay. So, the energy is fairly continuous with respect to distance. In a quantum well, these carriers are confined in one direction, say they can be confined in the x direction such that k becomes 0. So, they lose their momentum in this direction. The energy within the well is no longer continuous with respect to x direction, and hence it becomes quantized in these sub bands. So, within the whole universe of conduction band, you can have localized places which can be considered as sub bands, okay, which belong inside the conduction band only, okay, but then the energy profile is not continuous above E c. Right. So, you can have localized regions of barriers inside the conduction band, which electrons in a particular direction fail to cross. So, they lose momentum in that direction. The most important parameter to study quantum well are the length of this well and the height. By height we mean the energy height or the energy barrier height. Okay. This much is the amount of energy which must be available with the electron, so that it can surmount this localized potential well. Okay. So, due to this confining nature, now you can relate this discussion of quantum well to the discussion of infinite potential well. Okay. When we studied infinite potential well, we saw that the energy was a function of the length of the well. So, here also we do the same thing. We solve Schrodinger's equation in a quantum well such that the wave function psi in that particular direction. Now, we are saying that out of the 3 dimension in the x direction you have this confinement. Okay. So, in the x direction the wave function is quantized sin n pi x by L, L x is the length of the well. Okay. N is integer, okay. X basically measures the distance only. The pinning of nodes at the well boundaries leads to the quantization of energy at these subbands. The minimum energy in each subband with respect to the edge of the band is proportional to square of n and inversely proportional to square of length. Okay. This is similar to discretization of energy or quantization of energy inside a potential well. For confinement, this energy has to be higher than k T, Boltzmann constant. Now, this k is the Boltzmann constant. So, I should rather write it as k B T. Okay. So, just for differentiating between these two, this is not your wave number, this is the Boltzmann constant. Okay. So, when this energy is higher than Boltzmann constant time temperature, your so called thermal energy, and when the length of this well is less than lambda p or mean free path, okay, and this Lx is also less than the de Broglie wavelength, we can say that confinement has occurred. Okay. So, electrons are confined in these subbands provided this energy and length conditions are verified. Many modern semiconductor devices exploit this property, they work on quantum wells. Okay. So, the continuous conduction band is now divided into subbands. So, carriers we cannot say that they reside on the band edges, but they can reside in these subbands. So, confinement occurs within these subbands. The effective energy gap now is difficult to say that it is going to be equal to E c minus E v. Okay. because if electrons are no longer at EC, or when they come back to valence band they no longer stay at EV, this definition of forbidden energy band gap inside this kind of a heterojunction, the quantum well, starts to lose some relevance. Okay. The effective energy gap now for these interband transitions, it becomes larger than the bulk energy band gap. Okay. So, that was the concept of quantum well. When these quantum wells are separated from one another by a thick barrier. Okay. So, now we are talking about thin and thick barriers. By thickness, we are just meaning by the distance between them, between two successive wells you can say, okay, or the walls of these barriers are quite thick. So, to make a transition from one well to another, there is no communication between successive quantum wells, okay, and this system can only be understood as a series of individual quantum wells which are multiple in number. Okay. When the barrier layers between them start to become thin, their individual wave function can start to overlap. Okay. As we know, every potential well is characterized by a wave function, and this wave function gives different values related to energy momentum of the charge carriers which are confined in these wells. Now, their wave functions start to overlap. This kind of arrangement is known as super lattice. Okay. So, quantum well is a type of a heterostructure and super lattice is a type of a quantum well. So, you can say that super lattice is also a specific type of a heterostructure, right, where the walls, the thickness of the walls of individual quantum well is very thin. So, the wells can communicate with each other via their wave function which start to overlap. Okay. Discrete levels are, these are your so called, okay, super lattice formed from these discrete levels inside the continuous conduction and valence band. Right. The super lattice has two major differences from your multiple quantum well system with thick walls, that the energy levels are now continuous in space across the barrier because their wave functions are now overlapping. So, this is slightly analogous to the tunneling effect also, where the wave function tends to be present outside the barrier. Okay. So, in a potential well, if the wave function exists outside the barrier, we say that tunneling can take place. Similar to this structure here inside your energy bands, where you have quantum wells, if they are very thin, you produce a structure known as super lattice. Okay. So, now since wave functions start to overlap, you can say that energy is no longer discrete, but follows a continuous variation across the barrier. Okay. And the discrete bands, now they widen into so called mini bands. Okay. The transition from multiple quantum wells into a super lattice is analogous to the formation of a regular lattice by pulling atoms together. So, one well connected to another, to another, to another. The isolated atoms, they have discrete levels. A lattice transforms these discrete levels into continuous conduction and valence band. Okay. Apart from these two, quantum well and super lattice, you can have another structures which are quantum wire and quantum dot. Okay. Now, these are related to the dimensions in which we are measuring. Right. The physical dimensions, they have significant implications when it comes to semiconductor devices. When these dimensions are reduced to the order of wavelength, de Broglie wavelength, the confinement of carriers can be further extended into lower dimension like in 1D or 0D, okay, resulting in what is known as quantum wire in 1 dimension and quantum dot in 0 dimension. So, in bulk semiconductors, we are talking about 3 dimensional arrangement of energy bands. When we talk about say quantum wells, you can say we are talking in terms of 2 dimensions. Okay. In quantum wire, we are only interested in energy profile across 1 dimension, and quantum dot is basically related to a simple dot in space, which is not expected to have any dimension in either of the directions. Okay. One of the major effect happens on the density of states. This is the symbol for density of states. Okay. If you remember our discussion on carrier concentration, density of state is number of energy states available per unit energy per unit volume. These are the states which are nothing but solutions of Schrodinger wave equation. These are the energy levels which are expected to be discrete. Okay. These are the energy levels which charge carriers can occupy. Okay. So, electrons can occupy these energy states, but depending upon the dimensions you can have different value of these density of states. Okay. So, for a 3-dimensional system, we had seen in one of our earlier lectures that the number of states available in a 3-dimensional crystal lattice is proportional to the square root of energy. So, if we go above E c, you can say that the number of energy states available tends to increase as you go higher on the energy axis. Okay. And the probability of finding electron also goes down. So, in a way you multiply these two things to get the carrier concentration, but the discussion here is only focused on density of states. So, number of states available per unit energy per unit volume in a 3-dimensional system is proportional to the square root of energy. In a 2-dimensional system, it is independent of energy. Okay. So, this can be related to your quantum well. In a 1-dimensional system like quantum wire, as energy increases, the number of energy states available goes down, okay, because density of state is inversely proportional to the square root of energy. And for a 0-dimensional system like your quantum dot, it is proportional to only the differential energy present at that point or at that dot only. Okay. So, with the dimensions, the number of available states goes down, and we know that the carrier concentration is obtained by multiplying two things: density of states and probability of electron occupancy. If the density of state is varying with energy, the carrier concentration is also going to vary. Okay. So, in these dimensions you are going to have different values of carrier concentration. Number of charge carriers available per unit volume is going to vary with dimensions, and if the concentration of charge carriers is going to vary, charge is going to be different and current is going to be different from these different devices. Okay. That is the purpose of studying these different properties of semiconductor materials. Okay. So, this is a pictorial comparison. In 3 dimension, we can say that density of states varies directly with square root of E. In 2D, in a particular say a region of confinement, density of state is constant with respect to energy. After the localized barrier, there is another level of confinement, then after a certain barrier there is another level of confinement, but in that particular well subband, the density of state is constant, it is not related to energy. Okay. In 1 dimension, you can say that it reduces and then it remains constant, and then it reduces, then remains constant, then reduces. Okay. In 0 dimensions, it is only proportional to that differential energy at the point of analysis. Okay. So, this is the discussion which we have now completed on the different properties and different type of heterostructures which you can have from semiconductor devices. Now, when you use these different structures of different dimensions in a device, the level of current, the level of defects or various other parameters which are related to analysis of semiconductor devices, these are going to change. Okay. So, that is the main objective of studying these properties, that you are able to relate them to the final device. Okay. We will now move our discussion to something known as transport equations. Carrier transport is something which we have discussed in detail. We are just going to make a small discussion and summarize your basic equations which are responsible for conduction of current in a semiconductor device. Okay. The basic equations, these describe the static and dynamic behavior of carriers under external influences and also at equilibrium condition. Okay. So, you may have applied external electric field, there may be source of optical excitation available, okay, or the semiconductor might just be at thermal equilibrium. These equations are going to describe how the charge carriers, your electrons and holes, are going to move inside the semiconductor. These are classified into 3 groups known as electrostatic equations, okay, current density equations and continuity equations. Okay. So, let us just briefly discuss all 3 of them one by one. Electrostatic equations, if you remember one of the Maxwell equation, del dot D, D is displacement vector, is equal to the charge density, charge times the concentration. Okay. So, you have rho bulk density in all 3 dimension, D is known as displacement vector, which is related to electric field, okay, and is medium dependent. So, displacement vector is equal to strength of electric field times epsilon, epsilon is relative permittivity. Okay. So, del dot E becomes rho by epsilon, okay, and electric field is gradient of potential. So, E is equal to minus dV by dx or minus d phi by dx, you can say, since electric field is minus d phi by dx. This equation here, this can be written like this. Okay. So, del square phi equal to minus rho by epsilon. This is also known as Poisson equation, quite commonly known as Poisson equation. Okay. So, this equation basically tells you how potential and consequently electric field varies with respect to charge density. If your material is constant, okay, if your permittivity does not change, the level of doping can affect changes in charge density. Okay. So, this equation, and since it is dependent on potential, electric field and charge density, it is categorized in the category of electrostatic equation. Okay. Next we have current density equation. This we have derived already when we were discussing carrier transport. The total current in any semiconducting material, since semiconductors are bipolar in nature, they have both electrons and holes, both can be present at the same time in a semiconductor. One will be in majority, other will be in minority, depending upon the polarity of the device. Okay. So, since both are present, current will be produced by both. So, you will have current density because of both electrons and holes, plus you can have current from 2 different mechanisms. You can have drift of charge carriers, you can have diffusion of charge carriers as well. Drift happens when there is an external or an induced electric field present. Diffusion happens whenever there is a concentration gradient present. So, total current density is sum of drift and diffusion. Drift can be produced by electrons and holes, diffusion can be produced by electrons and holes. This is the equation for drift, electron drift current density, this is hole drift current density. Okay. This is electron diffusion current density, this is hole diffusion current density. Okay. And this you can also write it in terms of gradient of Fermi level, okay, in N and P type semiconductor. Mu is mobility, E is electric field, EF is Fermi level, N is electron concentration and P is hole concentration. Okay. So, these are your so called current density equations. Lastly, we have continuity equation, which is nothing but equation of charge conservation. The amount of charge which enters any cross section of a semiconductor, the rate at which this concentration changes. Okay. Whenever you apply external source like light, heat or electric field, you produce excess charge carriers. These excess charge carriers tend to increase the minority carrier concentration in any semiconductor. The rate at which these excess carriers are generated is equal to how much flux enters a semiconductor minus how much flux of charge exits this semiconductor plus any generation minus any recombination. Okay. So, that is why it is known as an equation of charge conservation. So, the rate at which excess carrier concentration varies is equal to how much flux of these charge carriers enter minus how much leaves this semiconductor, or you can also talk about a particular cross section, plus if there is any generation which has taken place minus any recombination. Okay. So, the rate at which say electron concentration changes, okay, by rate we mean rate of change of carriers per unit volume. Okay. So, this is number of electrons per unit volume per unit time is equal to 1 by q rate of change of current density, not the rate, sorry, the change of current density with respect to distance, incoming flux minus outgoing flux, plus any generation, Gn is rate of generation, okay, minus rate of recombination. Okay. So, this is the rate of recombination, okay, excess carriers, excess carrier concentration divided by the lifetime of excess charge carriers. Okay. Similarly, for holes we can write the same equation. Okay. This minus sign usually appears itself because in the diffusion current density for holes you have a minus sign. Okay. So, this is the third set of equation. So, you have electrostatic equations or Poisson equation, you have current density equations which include drift and diffusion current density, plus you have continuity equation which is nothing but equation of charge conservation. These three equations put together are known as your carrier transport equation, and they describe the behavior of transport or movement of charge carriers and hence current density in a semiconductor. Okay. So, this is another variant of your continuity equation. This is the application. It can be used to estimate the decay of excess carriers with time and with distance. This Lp you can also write Ln, this is the diffusion length, the amount of distance your excess charge carriers travel before they recombine. Okay. So, at time t equal to 0 you have an equilibrium concentration plus whatever happens because of generation. At x equal to 0 you have an equilibrium concentration plus this at x equal to 0, this is at equilibrium, this is at x equal to 0 and exponentially dependent on distance. So, charge carriers concentration, excess concentration decays with respect to time and distance. This is an application of continuity equation. Okay. So, with this we come to the end of today's lecture. These are some of the references which you can refer to see the content of today's lecture. So, we have seen some of the specific properties related to nanostructures, and we have also discussed some of the basic transport equations. Okay. Thank you for watching this lecture.